At the end of the analyze phase, you brainstormed a list of potential causes of variation. These are the candidates for the position of vital X. In Step 7, we do further analysis on these candidates and select the winner or winners for the vital X designation. The fishbone or cause and effect diagram will help us link these potential vital X's to the targeted effect, our Y. Click Next and we'll take a look at our learning objectives for this step. Let's quickly look through the Step 7 learning objectives. We will identify the vital X's for a given Y. We will also select the appropriate improvement strategy based upon characterizing the X's as either operating parameters or critical elements. We will review the applicability of a statistical technique called design of experiments, or DOE, which allows us to test causality and which provides a solid statistical foundation to identify which factors are the vital X's. Design and execute a screening DOE with factorial designs, and define, describe, and explain the significance of a lurking variable. So click Next and we'll get as a result of our brainstorming of potential X's. The team started analyzing the individual factors with an eye to narrowing down the choices for our project. Click Next and we'll discuss the results. The fishbone exercise is the first part of a brainstorming session. It serves as the container for all suggested factors. The second part of brainstorming involves tapping historical data, process knowledge, and process documents to eliminate as many factors as possible. Any factors not conclusively eliminated will be tested with a technique called design of experiments to validate their significance. The first area they looked at was the environment branch. The supervisor had checked records, including an analysis of the work area done by a human factors engineer, and felt comfortable in ruling out all of these areas. The team then turned its attention to the questions of GE personnel and customers. Nobody could find any correlation between the factors listed and any aspect of the cycle time, so all of these items were dropped. There have been no reported problems with customer interaction, and no evidence that customer input on the loan forms has any impact on overall performance. So this left methods and missing data. First, the team looked at the methods. According to several of the managers, neither the subclassification nor the prioritization had any impact on the cycle time. After deleting this topic, we were left with only one major area, missing data. Click Next to continue. Within the broad topic of missing data, we looked at 4 possibilities for vital X's. The question of form layout was quickly dismissed as unlikely. Font size was accepted as a possibility, at least worthy of testing. The question of whether to keep paper forms or standardize on all electronic forms had come up many times, so the team felt that this would be a good place to test the effect of that change. Finally, the team decided to determine if highlighting all required fields in the form would aid the GE associates in properly completing their task. So we have refined our list to 3 candidates. Take a moment to think about them, and we'll look at a couple of questions. Click Next when you're ready to continue. Let's take a quick look at how we characterize vital X's. Critical elements tend to be changed by changing the kind or type of element, as opposed to changing an amount. These are X's that are not necessarily measurable on a specific scale, but have an effect on the process. Some of these changes would include alternative workflow sequences, process standardization, and other qualitative changes in the process. Vital X's, which are critical elements, require testing of alternatives in order to determine the best solution. Operating parameters tend to be changed in amount rather than replacing an element with another. These are X's that can be set at multiple levels to study how they affect the process Y. Some examples include the speed at which bills are sent through a processing line, pressure applied by a machine stamping out credit cards, or the amount of memory available to a specific application. Operating parameters call for a mathematical model which helps you find the optimal setting for the vital X's to address the CTQs. Click Next to continue. Let's see how you do on this one. One of our candidate x's is an operating parameter, and the other is a critical element. Drag each of the elements to the appropriate box. Click on Done to submit your response. The change to total reliance on electronic forms is a process change with no intermediate settings, so it is a critical element. The change in font size is a how much type of change, which is an operating parameter. You probably noticed that all of the potential vital x's were in the missing data fields area. Before we go any further, let's explore the link between missing data fields and the data entry cycle time. We have gathered 50 examples where we have the actual number of missing data fields and the corresponding data entry time in hours. Let's observe the relationship between the number of missing data fields and the corresponding data entry time. Click Next to continue. From the Mini-tab menu, select Graph and then Plot. The default plot will be a scatter plot of the data we indicate. Our data is in columns C2 and C3. We will put the number of missing data fields along the y-axis and the data entry cycle time in hours on the x-axis. This screen shows our data properly selected for the graph. All that is left is to click on OK to generate the plot. This plot shows a linear relationship. As one factor increases, the other increases as well. Our next step is to conduct a regression analysis to further quantify the relationship. Click Next to continue. First, select the Stat menu, and then Regression, and Fitted Line Plot. Click Next to continue. We first determine which variable will be the response. To do this, place your cursor in the Response Y field and click on column C3, the data entry cycle. When you click on Select, you are then telling Minitab that this is the data you are looking to change as a result of a change in another field. Likewise, you select column C2, Missing Data Fields, as the predictor, or the data whose change will trigger a change in the response. We are going to do a linear regression, which is the default, so we won't change that factor. The next thing we need to do is look at the options by selecting that button. Click Next to continue. We will leave the log 10 boxes both unchecked. In order to get as much information as possible from the plot, we'll ask Minitab to display both the confidence bands and the prediction bands. The confidence level, as discussed in the hypothesis testing, is left at the 95% default level by convention. When you click on OK, you'll be taken back to the previous screen. Pressing OK from that screen will generate the results. Click Next to see those results. While this is not a course in statistical analysis, this graph does establish a relationship between missing data fields and the overall data entry cycle time. The regression equation is y equals 16.9354 plus 7.12198 times the number of missing data fields. That means the data entry cycle time, or y, measured in hours, will be defined by that equation. Let's round it off to whole numbers. If we take our target of 48 hours and subtract 17, we have 31 left. Dividing 31 by 7 gives us an answer of 4.43. So as a rough estimate, we can say that the data indicates that for us to meet our target of 48 hours, we should average no more than 4.4 missing data fields per application. Click Next to continue. The approach we will use to test the significance of the suggested vital x's is called a design of experiments, or DOE. DOE is a statistical approach to test the significance of x's and interactions between and among x's. There are two general kinds of DOEs. A screening DOE is used in Step 7 to identify the vital X's for the CTQ. It looks at all of the variables or factors to determine those that affect our CTQ. Thus, it allows us to focus on the vital few and avoid wasting time on the trivial many. In the case of continuous data, the screening DOE may not provide the information necessary to determine the exact change required. In those cases, the optimization DOE is used in Step 8 to determine the optimal settings for the vital X's. These settings are identified through what is called the transfer function, which relates the customer specifications to specific settings for the vital X's. Now we'll look at some key considerations in our DOE. Including the current process conditions or baseline is a standard practice for doing experiments. Two benefits of this practice are: it allows you to compare experimental results with real-world process data using the same parameters, and by doing so, validates your experimental setup. Remember, you obtained baseline data in order to generate your original process capability report. Let's look at another key consideration. Another key consideration is the overall statistical design approach to your experiments. A full factorial design requires you to test every combination of factors at all levels. If the number of runs required to execute a full factorial design is too large to accommodate, reducing the number of experimental runs is inevitable. Statistical approaches, such as fractional factorial design, can provide an effective way to reduce the number of experiments while remaining aware of potential shortcomings in the design. Click Next and we'll address the factors involved in defining our experimental parameters. Another of the key considerations addresses a number of experimental factors. The number of factors to test is an outcome of the brainstorming session. In a screening DOE, which is what we are doing here, we will look at two different settings for each factor. This is typical of screening DOEs, where we are simply determining the vital X's. When we fine-tune our recommendations through an optimization DOE, more levels are typically used. Finally, we need to define the actual settings or the range of values over which we will test each factor. The range should be sufficient to ensure that we can detect any effect of the change, and it should also be feasible to carry out. Click Next and we'll look at some critical experimental design considerations. Another of the key considerations addresses the experimental setup. Replication is often confused with repetition. Repetition may involve additional observations during a single trial or run. Replication means to reproduce an entire experimental trial, but to do that under the exact same conditions each time. In order to minimize the effect of data gathered at a certain time or in a predetermined order, the order of trials should be randomized. All trials should take place under identical conditions, but that isn't always possible. Temperature, humidity, time of day, shift, individual supervisor, or technician are all nuisance factors that can be eliminated with a blocked design. Blocking variables is a technique which lumps all readings taken under identical conditions as part of a block. Click Next to continue.